Hello, have a good day. So we'll continue the design of clutches. Last class, in last video, you come across what is the meaning of clutch and what is its purpose and what are the different type of clutches you are going to get, as well as the difference between single plate clutch as well as multi plate clutch. So today we'll continue the torque analysis of a plate or a disc clutch. As we noted in earlier class, we are going to get two type of theories to identify the dimensions. Okay. So first one is what if a friction liner is new, then you go for uniform pressure theory. If you want to go for the worn out clutch or the worn out liner, then you go for the uniform wear theory. So let us consider a single plate clutch here, so which has a driving shaft, which is a disc A and a disc B here. Okay. Now disc A is attached with some lining material here, sort of friction liner. Now again it is connected to driving shaft. Okay. So now let us consider a disc which has an inner diameter is inner radius is Ri and outer radius is Ro. Let us consider a small strip of width dr, which is going to be located at a distance of r here. Which is going to be located at a distance r. Now let us look at the real clutch plate, how it is going to be analyzed. The diameter which is there from inner to inner, okay. This diameter is noted as an inner diameter. Okay. The diameter of its outer surface, extreme surface, it is noted as the diameter DO. And we are going to get a one more diameter here, that is what a mean diameter. That is what mean diameter. Noted with the letter dm. Outer diameter is do and inner diameter it's what a di. Now this is a portion, so where you are going to get a friction lining material here. Now if you consider W as the width of the friction lining material, then you can get the W as a dO minus di divided by 2. That means, so this is what the width W. Okay. Now we'll go for the theory of uniform pressure theory. Uniform pressure theory. So let's consider a view, side view of a clutch plate, okay, which has a diameter di and which is diameter, outer diameter as a do. And let us go for a mean diameter. This is what dm. Okay. So let us go for side view here. Okay. Now as say uniform pressure theory, the pressure which is going to exert on this friction material is of same intensity. That is what, if we consider pressure at inner diameter as well as pressure at outer diameter, it has to be same. Now to make engage and disengage, so you need to apply some axial force. As I said, we just consider a small strip here. Of width as dr, which is going to be located at a distance of r from center. Okay. Now consider a elementary ring of thickness dr, okay, at a radius r as shown in the figure. Now area of elemental ring. Now area of this elemental ring, if we consider this as an elemental ring which is at a distance of r. Now area of this elemental ring dr. So if we consider dA as elemental ring, what will get 2 pi r, okay, into dr. Now the axial force which is going to act on the elemental ring So let us take this as a DFA. Now I will get P into area, that will give the load, P into area will give the force. Now let us substitute the equation of area, what we got from earlier. Now P is what? It is the pressure intensity, okay, 2 pi r into dr is the area. Let us notify this as equation number 1. Now as we are using a frictional material, okay, now little amount of frictional force is going to act on the elemental area, that is what elemental ring, okay. Now frictional force on the elemental ring, so what will get? The frictional force, let us it as be represented as a DFF, okay. So now this is equal to what? F into DFA. So for F equal to, you can consider mu, this is what? Coefficient of friction. This is what coefficient of friction. Okay. Now let us substitute the value of dFA. If we consider mu as coefficient of friction, dFA equal to what? 2 pi into R into dr. Let us simplify this as equation number 2. Now, the frictional torque on elemental ring this is equal to what? So if you consider dt as a frictional torque on elemental ring, so how will you get torque? It is what radial distance into the frictional force. Now let us substitute the frictional force. This is what mu into r into 2 pi, okay, into p into dr. So now to get the torque, now dt equal to 2 pi mu, okay, into p into r square into dr. Now to get the torque, that is what a complete torque which is going to act on the disc because of the friction. You will get integration from Ri to R naught, okay. This is what 2 pi mu p r square into dr, r square into dr. Now rewrite the equation for axial force. Now this is what axial force Fa equal to integration from R naught to Ri to R naught. So what 2 pi r square into dr into mu, now divided by r. If we rewrite for the axial force, what will get? The Ri to R naught 2 pi r dr into mu. Now take out a constant term outside here, 2 pi p as well as mu. 2 pi p as well as mu are a constant term. So now the variable terms are only r into dr, r into dr. So now let us integrate. What do we get? 2 pi p mu r square by 2 limit Ri to R naught, Ri to R naught. Let us substitute here, or the frictional force Fa equal to 2 pi p mu divided by 8 dO square minus di square. Now again, which equation yields pi p mu dO square minus di square all divided by 4. So now this is what Excel for calculations are required to engage and disengage the clutch. So now regarding torque transmission capacity or torque transmission, so based on the friction, we got dt equal to, let us integrate dt equal to what I got earlier, 2 pi mu into p into r square into dr to get the total torque which is going to act over the disc clutch. This is what integration Ri to R0. This is what 2 pi mu p r square into dr. If we simplify this equation, now the frictional torque T equal to 2 pi p into mu into r cube by 2 in the limits r cube by 3 limits Ri to R0. Now let us substitute boundary condition. Torque T equal to 2 pi p mu R0 cube divided by 3 minus Ri cube divided by 3. So now this equation can be rewritten if you substitute the value of R0 as the D0. What will get? 2 by 3 pi mu p into D0 cube minus di cube. D0 cube minus di cube. Now if you put the equations for the torque as well as for axial pressure, you are going to get a 2 to 3 unknowns here. You are going to get a 2 to 3 unknowns. Now let us substitute value of pressure as in terms of axial force. So because pressure P equal to what? Force by area. Pressure P equal to force by area. So if you consider P as a pressure intensity, this is what Fa divided by area. So Fa is the friction force. Area is what? It is pi R0 square minus Ri square. Let us substitute in torque equation. What will get? T equal to, we substitute pressure in torque equation. What will get? T equal to 2 by 3 into pi into mu into Fa divided by pi r naught square minus Ri square into, okay, so we need to substitute in terms of r naught here. Let us substitute r naught cube minus Ri cube. So if you further simplify, substituting value of r naught and Ri in terms of d, what will get? 2 by 3 mu into Fa d naught cube minus di cube whole divided by 8. Again this divided by d naught square minus di square divided by 4. Let us substitute. What will get? T equal to 1 by 2 into mu into Fa into dm. So now dm is what? It's the mean diameter for uniform pressure. So now dm equal to 2 by 3 do cube minus di cube do square minus di square. So this equation is available in the Alexander Handbook, equation number 13.9c. Okay? 13.9c. Now torque can be calculated by using equation number. This is what torque can be calculated using equation number 13.9 b here. So by this equation you can calculate either mean diameter, either torque transmission capacity.